Hey everyone, this video goes over the 2009 AP Physics C Mechanics for Response question number 2. So the question asks, you're given a long, thin rectangular bar of known mass m and length L with a pivot attached to one end. The bar has a non-uniform mass density and the center of mass is located a known distance x from the end with a pivot. You are to determine the rotational inertia I of B of the bar about the pivot by suspending the bar from the pivot as shown above and allowing it to swing. Express all algebraic answers in terms of IB, the given quantities and fundamental constants. Okay, so part A has two parts. The first part says, by applying the appropriate equation of motion to the bar, write the differential equation for the angle theta the bar makes with the vertical. So I have here two equations written for torque. The first one is torque is equal to I alpha, where I is equal to the moment of inertia and alpha is angular acceleration. The second equation for torque is R cross F. Torque is equal to R cross F, which is equal to RF sine theta. Both of these equations are given by definition of torque. So this R of sine theta. R is the distance from the pivot point to the force. F is just the force. Theta is the angle between R and F. You can understand that better if you look at this diagram. So we have one force here, the force of gravity. I'll get to that in a minute, but for now, just to understand what this equation really means, just assume that the force is right there. And this is the pivot point as given in the question. So the distance from the pivot to the force, that's just x, right? So R is going to be x in this case. F is going to just be mg. That's just one force that we're taking into consideration. There's no other forces acting on this. And then theta is the angle between x and f. And what I mean, so if you want to imagine that, right, you can take this f and put it up here at this pivot point, and then this angle between this sort of imaginary force. This is not really a force, but we're just putting this force of gravity here and putting it at the pivot to find out what the angle is. So pretend that the force is there. So the angle between this x and this f is theta. So that's what they mean by this theta here. Just the angle. So RF sine theta can be written as mgx sine theta. There's this negative sign here, we'll get to it in a minute. You might be wondering why we're not worried about any force that the pivot might have on this rod. So what we think about for torque, the formula for torque is RF sine theta. So if there was a force from the pivot, it'd be pointing this way, right? It'd be along the rod towards the center. If you look at this equation, R is going to be 0 because a force from the pivot would be originating from right there. R would just be 0. So the torque exerted by the force from the pivot is just 0. That's why we don't have it in this equation. And that's why the only equation we're worried about is mg, or the force we're worried about is mg. And another thing, we're not saying mg, so it's given in the question that the center of mass is right there. So that's basically saying, imagine that all the mass is at the center of mass, because that's what the center of mass is. It's asking you to assume that all the mass is centered right there. So that's why the force of gravity is from here, right? And you can't just say like mg wherever, like L over 2 or L, because it says it has non-uniform mass density. So the center of mass, if it's right there, mg can be taken as originating from this point, the center of mass, and then obviously the distance from here to there is x. So mgx sine theta. So there's this negative sign here. Why? So if it's saying that, this rod is swinging back and forth. If we have this rod from right there, and we're going to drop it, theta is going to decrease, right? It's going to go like all the way here, and it's going to the point it becomes vertical, and theta is going to be 0. So theta is going to decrease, right, when it's falling from here to here. And when theta decreases, that means that the angular acceleration is 0, or not 0, sorry, it's negative, right, because it's the double derivative of theta with respect to t. And what that means is if theta is decreasing, the angular acceleration is negative because this value is negative. It's decreasing with respect to t, and that's why we have this negative sign here. You could have also written it here, it doesn't really matter, because either way there's a negative sign, as long as there's one negative sign on either side of the equation. So yeah, that's what this is. Negative mgx sine theta is equal to I of v. I of v is just given in the question as a rotational inertia. And then we have this term, this is which, by definition, alpha is equal to the double derivative of theta with respect to t. Okay, so part 2 says, by applying the small angle approximation of your differential equation, calculate the period of the bar's motion. So first off, the small angle approximation basically says that theta is so small that sine of theta is equal to theta. It's just an assumption. It may not always be true, but it's telling us to say that here. So sine of theta is equal to theta. So what that means is that in this equation, we can replace the sine of theta with theta. So minus mgx theta is equal to I of b, or I of d squared theta over dt squared. So we can add this to this side, okay? So I b d squared theta over dt squared plus mgx theta is equal to 0. And the reason we want to do that is because the general equation for motion, such as this one, where it's rotating, or not rotating, but when it's swinging back and forth, any sort of like swinging motion or harmonic motion has this general equation where this is alpha d squared theta over dt squared plus omega square. Omega is the rotational velocity times theta is equal to 0. Okay, that's just a general equation that's given for motions such as this. And so we want to bring it to this form. Okay, and we're almost there. We just have this IB right here, and we can get rid of that by dividing it on both sides. This side's always going to say 0. We're going to have mgx over IB. So I just have right here, you want to see this? This equation is just where IB is divided on both sides. So now we have this mgx theta over IB. So now we're starting to look a little like this equation. It's actually pretty much the same thing. We just have different coefficients for theta, and that's fine. That helps us because we have the coefficient for theta here is omega squared. So, and the coefficient for theta here is mgx over IB. So we can just make those two equal to each other. Omega squared is equal to mgx over IB. Right? Make the coefficients of theta equal to each other, and then solve for omega. And why do we want omega? It's because it's asking for the period of the bar. And the period of the bar, the general equation for period is equal to 2 pi over omega. So this is important to us because we can plug that in right there. And then we can get a period of 2 pi times the square root of IB over mgx. So that's how you solve that problem.